Welcome back. We are on Unit 4, Derivatives of Exponential and Sinusoidal Functions. Lesson 2, Derivatives of Sine and Cosine Functions. In Lesson 1, we looked at rates of change of the sine and cosine function. Today what we're going to do is look at our derivatives rules and apply them to sinusoidal functions. So we can use the same steps that we had used in polynomial functions to sinusoidal functions. We can use such rules as the chain rule and the product rule in differentiating these functions. So example number 1, what we have, we have y is equal to 3x. Notice that the 3x is actually inside the cosine function. Okay, it's not actually being multiplied to cosine, it's inside the function. B, what we have is f at x is equal to 2 sine pi x. Again, pi x is inside the sine function, and 2 is a coefficient that is being multiplied to sine of pi x. Looking at example 1a, where y is equal to cosine of 3x, we want to derive with respect to x, which is an independent variable. Let's see how this is done. Remember that 3x is actually inside the function. So if you wanted to, you could put brackets, but in this case, usually the proper form is not to put it in brackets. Okay, you would always just assume that this 3x is inside the function. It's part of the function. So let's see how we can use the chain rule in order to solve this. Let's do it the long way, and after a while, as we've done in the past, we can skip all these steps. Okay, so we're going to say that u is equal to 3x. Okay, so I just want to just write out the chain rule again, okay, because it might be a long time since we've used this. dy by dx, or du, is times by du by over dx. Okay, all right, so what we have now is y as a function of u is cosine u, okay? And if we said that dy by du, we know this now as being negative sine u, okay? Over here we have u is equal to 3x, so du by dx is then equal to just 3, okay? So if we wanted to find dy by dx now, we would take dy by du, okay, and multiply by du by dx. So negative sine, and I'm going to make my substitution back in just so that the function is now with respect to x rather than u, 3x, and I can just write it like so. I'm going to use brackets here because we've kept the order. Okay, so just to rearrange and make it look a little bit nicer, we can simply say it is negative 3 sine of 3x. Okay, and there's our derivative. Moving on to b, f at x is equal to 2 sine pi x. Now let's try and do this one without having to make our substitution. Okay, so if I wanted to find f prime at x, okay, so the derivative of the sine function, okay, and the 2 is just a constant, we can just pull that right out. So the sine pi x, okay, is cosine. So the derivative of sine x is cosine x, but it is pi x, so it's cosine pi x, okay, and don't forget about the pi. Whatever is in the function, if you're deriving it, stays within the function. Now we take a look at what's inside the function, applying our chain rule. Okay, applying our chain rule, we're going to derive pi x, which would then, I'm just going to use brackets so it doesn't get confusing. It's just pi, okay, rearranging, 2 pi cosine of pi x. And don't forget to drop your pi that is within the cosine function. Okay, and that's our derivative. Let's look at using the power rule in order to derive sinusoidal functions. So example number 2, a, y is equal to cosine x cubed, b, y is equal to 2 sine x cubed minus 4 cosine x squared. So example number 2a, we have y is equal to cosine x cubed. Now, for those of you who have not seen this notation before, basically it's just a nicer way of writing it. It is also the same thing as saying cosine x cubed, okay, same. It's just that they like to put it up here. Doesn't mean that the x is actually cubed, it just means the entire cosine function is cubed. It just looks nicer. I think math people just prefer it. I'm not really sure why, but that's just the case. Okay, so let's take a look at how we're going to do this. So what we would do here is use our chain rule, or what we call the power rule. I didn't use that term power rule because we just used the chain rule. I felt it was more important for you to learn the chain rule than to just come up with all these extra rules. So dy by dx, what we're going to do is just bring down the exponent of 3, okay, and then it'll just be cosine squared x, because remember we subtract 1 from the exponent, and then we would derive what's inside the bracket, which is cosine x. Okay, so we multiply that with what's inside the bracket, the derivative of the inside, which is negative sine of x. Okay, negative 3 sine x cosine x. Now in working with sine and cosine functions, remember to always look to see if there's anything that we can do in order to simplify. So sometimes you can actually use identities. There's only a few identities that we're going to actually look at in this course, but I will give you a list of all the identities in case in your textbook you do encounter maybe a different answer in the back of the book or whatnot, because they've used identities in order to simplify. In the case of number 2a, this would be our final answer. So let's take a look at B. B, we said, was y is equal to 2 sine x cubed minus 4 cosine squared x. Okay, so in this case, I'm not going to change our notation just so that you can get used to looking at that. So we the dy by dx. Okay, remember there's two terms. Okay, can we do this all in one line? Let's try and do that. Okay, so what we're going to do is differentiate the first term, subtract it from the derivative of the second term. Let's do that all at once. Okay, so what we have is 2 is just a constant out front. Okay, I'm going to put a nice bracket. Bring down the 3. Okay, sine. Now subtract 1 from the exponent, which is squared x. I don't think I've left myself enough room here. I might have to go into the next line. Bracket, and the derivative of what's inside, so it's just cosine of x. Okay, and then we're going to subtract that, and I'm going to have to go on to the next line. So 4, bring that out front. 2, because of our exponent 2, we're going to bring it down. Cosine of x, bracket, and the derivative of just the cosine of x, negative sine x. Okay, so simplifying that, 6 sine squared x cosine x, negative times 2, which is negative 2 times 4, and don't forget to put this negative as well. Okay, so positive 8. And we'll go again, we'll just say sine of x. Doesn't really matter what order you put it in. Just to simplify, okay, the last step is to simplify. See if there's anything that we can factor. And so factor as best as you can. Looking at the coefficients first, I can factor out a 2, okay? I can factor one of the signs out, and I can factor a cosine. So let's do that. Sine of x, cosine of x, and then rewrite what you have left. I have 1 sine of x left. Looks like all I'm left with. And then I'm also left with, oh, and I forgot the 3. I'm just going to put that right in there. 3 sine x plus 4. Okay, so 2 sine of x, cosine of x, 3 sine x plus 4. Okay, so is there anything that I can do? Okay. So I've just quickly written out some of the major identities that we're going to use. I'm going to include in your lesson folder a list of identities that are important, but these are the main ones. So sine squared x plus cos squared x is equal to 1. That's the Pythagorean identity. Okay, and it's something that you might have learned in advanced functions or actually in grade 11. Tan x is equal to sine x over cosine x. So we're going to take a look at that a little further in the next part of the lesson. And sine, these are double angle identities. So sine 2x is equal to 2 sine x cosine x. Cos 2x is equal to cos squared x minus sine squared x. And there are other variations of it as well. Okay, so just a couple that I've sort of outlined right now. Other things that you can think about too is the reciprocal identities, which I haven't listed. Okay, so let's look over here. Now this would be a correct answer. However, always look to see, okay, number 1, always look to see if we can factor anything, okay? Number 2, is there an identity that I can use in order to simplify further? And sometimes your textbook will use the identities, so you'll find your answer, although beautifully done, might not match the back of the textbook, and that's probably because they've used an identity. Okay, so let's look at this case here. So what do you notice? Well, I noticed, the first thing that I noted was this right there. I noticed 2 sine x cosine x. Well, what I can do is actually use this identity to replace that. Okay? So I can now also say sine 2x, 3 sine x plus 4. Okay, and that would also be equivalent as well for dy by dx. Other cases will be where you'll have to actually use the identity in order to make it look more simplified, so before you even start differentiating. Okay, and that could be a possibility as well. You might encounter that, and when you do, try it out. If you have any problems, then of course, then you can just email me. Let's look at using the product rule in differentiating sinusoidal functions. So example number 3. We are looking at y is equal to t cubed cosine t. Okay, so in this case, our independent variable is t. So I've kind of thrown different ones because we don't want to get too used to always using x as our independent variable. Over here we have h of t is equal to sine 4t, and so 4t is within the function, and sometimes you will see it with a bracket, in other cases you won't. In this case, it is easier to put it in the bracket in order to identify that it is inside the sine function. And that's because we have it multiplied by sine t squared, okay? And it keeps everything a little bit more organized, but you will not always see the brackets. Looking at our first example, example number 3, the first function, we are going to derive with respect to t, okay? And again, t is our independent variable. So we can use the product rule. Okay. Product rule. Okay, so let's just do this the short way. Okay, so dy over dt. Okay, I'm just going to go ahead and do the product rule because I'm sure by now you're probably used to doing this. And you don't need to write out your f at x and g at x, but if you really wanted to, you can. Okay, don't feel that you have to do it my way. So f at x, and this is g at x. Okay, whatever makes it easier for you. So I'm just going to go ahead. So it's going to be the first, and again, order doesn't matter. So if you want to take the derivative of the second first, that's fine. So the derivative of the first is 2. Oh, I'm going to go with the first, which is t cubed. Okay, the derivative of the second minus sine t. Okay, plus the derivative of the first, 2t squared times the second function. There we go. Okay, so let's make this look a little bit nicer by Well, do you want to go ahead? Let's just go ahead and factor out what we can, which is t squared. Okay. Okay, I'm just going to do this step by step so that you can see. Okay. Although that is correct, I always like putting my terms that are negative second. Okay, so having a term that is positive first. And over here, I've made a mistake with 3, so we'll change that to 3. So 3 cosine of t minus sine t. And that's it. And I don't see anything else that we could actually do there. Okay, so let's move on to the next one, in which we have h at t is equal to sine 4t, cosine t squared. Okay, all right, so product rule, h primed at t. So we'll say the first, the derivative of the second. Okay, I'm using now my power rule or my chain rule. 2 cosine t minus sine t. So the derivative of the inside, okay? Yes, it's going to get very long, but you can do it. Okay, so the derivative of the first, which is 4, chain rule, cosine 4t. Okay. And then the second, cosine squared t. Okay. So let's simplify this so it looks a bit nicer. Multiplying this in, I'm going to bring this out front and multiply this. No, you can't really do anything with that. So let's see. So we'll just rewrite it for now. So in this case, it would be minus 2 cos t sine t, doesn't matter what order you have it in, sine 4t, okay, minus 4 cos 4t cosine squared t. Oh goodness, that is quite long. Okay, so is there anything that we can do here? Although that is a nice answer. Is there anything that we can factor? Well, let's see. I can factor out a cosine. Okay, I can factor out a cosine and also the 2. Okay, and also just to note here that I've changed that to a positive. I don't even know why the negative was there. That's a positive there, okay, and which makes this a positive as well. Okay, so let's go ahead and factor out a minus, nope, a positive, 2 cos of t. And because I have this minus sign here, I'm going to switch them, okay? So I'm actually going to put this term first. So it'd be 2 cos of t cos of 4t. So I've also just swapped these around. That's it. Okay, so minus now, minus 1. I'm taking the cosine out and the sine of t sine 4t. Okay, and that looks like our final answer. Is there anything that we could have maybe have used as an identity? Maybe simplifying these, but I think that we would actually make it more complicated if we use some of our double angle identities here. And I think that would be a final answer. Let's quickly look at the derivative of tan x, because I'm pretty sure your textbook goes through tan x. So we'll just quickly cover that. Let's note that tan of x is equal to sine of x all over cosine of x. Okay, so let's derive tan x. So if we said the derivative of tan x, so dy by dx of tan x. Okay, I just want to quickly change this over to sine of x. You can also use the quotient rule as well. Cosine negative 1x, okay? Quotient rule would also work. It's equal to, okay, so we're going to use the chain rule. So the first, sine of x negative cosine of negative 2x times sine of x. I've just used the product rule and power or chain rule here, plus the derivative of the first, which is cosine of x, and the second, cosine of negative 1x. Okay, so I'm going to factor out the lowest power, which in both cases we have cosine x, it's common, so we're going to actually factor out this lowest power here, cosine of negative 2x. Okay, and what I'm left with is sine x. I'm going to multiply in, so I have negative sine x squared, okay, plus cosine x, and then when I factor out a negative 2, I'm going to be left with another cosine x, so I'm going to have cosine squared x, okay. Okay, so one other thing to note here is there is a mistake here, so that should be a negative sine of x, okay, which makes this a positive. There we go. Okay, that should work out much nicer for us. So look at this here. What does that look like to you? So what we have is sine squared x plus cosine squared x is equal to 1. Okay, so that's our Pythagorean identity. Okay, so I'm going to replace that entire bracket with 1. Pythagorean identity. Okay, so here what we're going to be left with is cosine negative squared x, which is the same thing as 1 over cosine squared x. Okay, so remember that 1 over cosine x is actually equal to secant x. So what I can say here then is that is equal to cosine, secant squared x. Okay, so the derivative, so dy by dx of tan of x, then is equal to secant squared x. Okay. One last thing that we're going to do today is, of course, check our learning. So what I want you to do is to determine the derivative dy by dx for y is equal to cosine 1 over x. So make your decision now. And the answer here is, get a nice pen, is A. A, okay? So that's it for today, and we'll see you next time.